Okay, this is 13.7. This is on tangent plane approximation. And so let me start with a sort of a little introduction so we understand why this is relevant from an actual real-world point of view. So if you remember in Calc 1, we can do what's called tangent line approximation. And so what this is the following. So given a function and a point, so if you take your function, maybe it looks something like this. Maybe here's x0. So if you draw the tangent line at x0, that will look like this. This is the tangent line at x0. Technically, it's at x0 comma f of x0, because that's the y value. Keeping in mind this is f of x. This is the graph of f of x. We can make the following claim. If some other x is close to x0, then f of x is close to the tangent line. So in the picture, for example, if you have like an x that's right here, if you go up to the tangent line, those are close, right? The function is approximately the tangent line. And, of course, as x gets further away from x sub 0, the approximation gets worse, but it's a pretty good approximation, right? Now, you might think this is sort of goofy, like why would this be useful? But this is sort of the beginning of the process of Taylor series expansions, which are used heavily in engineering applications. And so the way that the whole process begins is, first we find the equation of the tangent line. Now, of course, we're not going to go full Taylor series here, but I just want to write this down so that it sort of rings a bell. Right? So then we say to ourselves, well, what's the tangent line? Right? So, well, the slope is f prime of x0, because that's the derivative, and the point is x0 f of x0. So the point slope formula says that the tangent line is y minus f of x0, this is a point slope formula, equals the slope times x minus x0. So in other words, sorry, it's kind of messy, y is equal to f of x0 plus f prime of x0 times x minus x sub 0. So then what we can say is, if x is close to x0, then f of x is approximately the tangent line. So that's sort of what happens, right? Now, where this plays into Taylor expansions, just so that you know, like I said, even though we're not going there, is that this step right here, this is the beginning of the Taylor expansion. So the Taylor expansion then adds more and more terms to this as we go like to a full Taylor series, which goes forever and ever and ever and gets an infinite series that converges, etc. So, like I said, we're not going to go that far, but what we do want to look at is like, well, what can happen here in higher dimensions? Like if you have f of xy, for example, can you do a similar thing? And the answer, of course, is yes. And you can do this with multiple dimensions. So we'll do it with f of xy. We'll figure it out. We'll find a formula. And then once we see that, we'll automatically see what happens with, say, f of xyz. So the first thing we'll look at is tangent plane approximation. So what I'll do is I'll draw a picture which will hopefully look like a two-dimensional version, or a three-dimensional version, if you like, of the picture on the left. Right? So here's the situation. Here's that, let's say, the visual situation. So instead of having an f of x, we have an f of xy, which could be, say, something like a parabola, because it makes for a good picture. So here is our f of xy. I'm not going to draw an axis for now. And then we have an x sub 0. We have a point down in the xy plane, which is, say, for example, this point. That is the point. That is x sub 0, y sub 0. Now, let me do this in the same colors as the other picture. So this leads to a point up on the plane, up on the surface right there. Now, what we get is not a tangent line anymore, but we get a plane. So we get a plane which is tangent to the surface. So this is what's called the tangent plane at the point x0, y0, f of x0, y0. That's the point. That point right there is this point right there. And so that tangent plane sort of sits tangent to the surface, right? And so what happens is we can make a similar claim. We can then say, well, look, if I take a point x0, if I take a point, say, xy, which is close to x0, y0, then f of xy is close to the tangent plane. And again, we can see that in blue. For example, we can say, look, if I pick something that's close to this point, like that's xy, if I go up to the plane, might be maybe about here, that's not going to be exactly on the function, but it'll be on the plane, it'll be close to the function. Right? So here, right here, the function is close to the tangent plane. So then this leads us to the obvious question, is like, well, look, if we believe all this, what is the tangent plane? In other words, like, what is an equation of it? So, i.e., an equation. Because it's only by doing that that we can go through this process that we did on the other side, right? So the whole rest of this, right here in pink, was actually figuring out the equation of the tangent line. And then we could make this claim that came at the end. So what we need to do is we need to do a similar thing for the tangent plane. We need to say, okay, great. What is the equation of the tangent plane? Once we know that, we're good, because we just say, look, the function is approximately that. So what I'll do is I'll clear the screen, and then we'll go through the derivation of finding the equation of that tangent plane. And it's going to be sort of similar to the tangent line. We just need different information. We know generally what the equation of a plane is. We just need to work with it. So let me clear the screen off and work through that. So we'll say finding the equation of the tangent plane. So let me redraw the picture a bit. So what I'll do is I'll draw the plane. I'll try and draw this really pretty so we can understand what's going on. That's the plane we're looking for. The surface that underlies it is like this paraboloid kind of thing, whatever it happens to be. There's a point that they're meeting, that the tangent plane is generated. Now, we know that point, right? That point is our point x sub 0, y sub 0, f of x sub 0, y sub 0. So we ask ourselves, what data do I need for a plane? So the answer is we need a point and a normal vector. You may need to look back at chapter 11 to remind yourself of that. We need a point, which we have, and we need a normal vector, which we don't have. So the normal vector on the picture needs to look something like this. It needs to be normal to the plane and normal to the surface. Really normal to the surface because that's how we're building the plane. So how can we find n? Once we've got n, we're home free. So here's the deal. N needs to be perpendicular to f of xy, the graph of f of xy. Right, like in the smaller picture, the guy that we're looking at, the normal vector that we're looking at, needs to be perpendicular like this. So that might ring a bell because that might remind you of what we did in the last section. And here is our z equals f of xy, or just f of xy. So in the last section, what we looked at is a couple things, but the very last thing that happened in the last section is we looked at the fact that if you have the gradient of a function of 3 variables, that gradient is perpendicular to the level surface, right? So in this case, since z is equal to f of xy, I really have a function of 3 variables, right? So the reminder here is that if we can express our graph as the level surface, of a function of 3 variables, then the gradient of that function will be perpendicular to that surface. And that comes from 13.6. So, right, our graph is z equals f of xy. This can be rewritten as f of xy minus z equals 0. Right? This guy, this thing on the left, this is now a function of 3 variables. It's equal to 0, which makes it a level surface. In other words, let's just be clear about that. It's a bit of a sloppy sentence. The function f of xy minus z is a function of 3 variables. And when that function equals 0, we get the graph of our surface. In other words, i.e., just to be clear, that the function of 3 variables, which is f of xy minus z, when we set equal to 0, we get z equals f of xy, which is our surface. So what that means is I can take the gradient of this, of that function of 3 variables, and that gradient is perpendicular to our graph, so it's our surface, so it's our normal vector. So let's find that gradient. All right, so that gradient, take the derivative with respect to x, which is f sub x, I, derivative with respect to y. Now, the z vanishes in both cases because derivative of z is 0 with respect to x and y. But when I do this final derivative with respect to z, I just get minus 1k. So this is our n. So, take a look. I'm going to circle some things. What we've got so far is we've got a point right here. We've got a normal vector, which is right here. So what that says is that we can put them together to get the equation of the tangent plane. Remember how the equation of a tangent plane works? I take the coefficients of the normal vector. Now, actually, let me be a bit sloppy here. Let me erase this because I need to say a bit more. So the other thing I need to say is this n, this is not quite. Because we need to know n at our specific point. Right? So at x0, y0, we need to plug in our point. So that's our n. Let me get rid of that circle, put it around here. This is the one we want. So I'm going to combine these two things. I'm going to clear the screen and I'm going to combine those two to create the equation of a tangent plane. And then we can write down our final formula and look at an application, look at an example. So we can say the following: thus, equation of the tangent plane. So remember how this works. It's the coefficients of the normal vector times x minus, and then the point coordinates. So again, if this doesn't ring a bell, you may need to look back at the section on planes, 11.6. And then we had minus 1. Well, I'll put plus minus 1. And then z minus z0, but z0 was our f of x0, y0. This is all equal to 0. So I'm going to solve this for z. Just like at the very beginning when we were looking at tangent line approximation, we solved for y. So here I solve for z. So we have a negative z, so I'll just move it to the right. I'll just write it the other way around. So when we do that, we get f of x0, y0 plus f sub x, x0, y0, x minus x0 plus f sub y, x0, y0 times y minus y0. Now, this looks really, really awful, but this should remind you of something. Right? This should ring a bell. Reminds us of this was the tangent line at the very beginning. So take a look at those two. They're very similar. Right? In the right-hand case, in the pink case, we've got f at the point plus the slope times the difference between the x's. In this case, we've got f of the point plus the derivative with respect to x times the difference between the x's plus the derivative with respect to y times the difference between the y's. So we've just sort of ramped it up to include this extra variable. So thus we can finally make a claim. So here's the final important applicable fact of this. If x comma y is close to x0, y0, then the function is close to the tangent plane. I'm going to rewrite all this. So that's the final conclusion that we get to use. And again, as before, this is the beginning of a Taylor expansion, like a two-dimensional sort of a Taylor expansion, which if you're a math major and you take Math 411, advanced calculus, second semester advanced calculus in general, you see how to expand this to go to higher derivatives, second derivatives, third derivatives, etc., just like the Taylor expansion does. So let's look at an example. So suppose I have something like f of xy equals the square root of x squared plus y. Let's use tangent plane approximation. To approximate f of 2, 5. Now, just the record, right? Like, in terms of actual engineering applications, you might say to yourself, well, look, if I really wanted to know, actually not 2, 5, that's not the, sorry. Let's do f of 2.1, 4.95. So just for the sake of perspective, right, in this day and age, you would literally just plug in f of 2.1, 4.95 into this function and figure it out. You could do it on a calculator, but then you might ask yourself, well, how does the calculator figure it out? Right? How does it do these kinds of square roots? What's actually going on under the hood? And so what we want to do is sort of figure out like how we can get a good approximation for this, right? Just by hand, how we can like computationally sort of figure out what's going on. So the one thing I want to notice is 2.1, 4.95 is close to 2, 5. And that's a particularly nice point. Like we can plug that into f very, very nicely. Because if I plug it in, we get the square root of 2 squared plus 5. It's the square root of 9, which is 3. So we're anchoring this at like a nearby nice point. So this is what the purple square tells us. This is what tangent plane approximation tells us. It tells us that since 2.1, 4.95 is approximately 2.5, then f of 2.1, 4.95 is approximately f of 2.5 plus f sub x of 2.5, 2.1 minus 2, that's x minus x sub 0, plus f sub y of 2.5, 4.95 minus 5. So really, all we need to do is find these things and plug them in, right? The three specific things that we need to find, one of them we already found is this one, and this one. This first one we know is 3. The second two we need to figure out, but they're not difficult. So we say, okay, f sub x of xy in general, derivative with respect to x. We have f above. This will be 1/2 x squared plus y to the minus 1/2 times the derivative of the inside. When we plug in our point, the 1/2 and the 2 cancel, so I get, let me tidy this up. I'll have a numerator of x, which is 2, over a denominator, which is the square root of 2 squared plus 5. That's 2/3. We have f sub y of xy is 1/2 x squared plus y to the minus 1/2 times the derivative of the inside, which is 1 in this case. So f sub y of 2, 5. So in this case, our numerator is just 1, but down says we have a 2 as well, and the square root of 2 squared plus 5, which is 1/6. So when all is said and done, we can say the point we were interested in This is approximately 3 plus 2/3, 2.1 minus 2. I'm going to leave this unsimplified just so it's easier to look at. Plus 1/6, 4.95 minus 5. That gives us a reasonably quick, reasonably nice approximation of something that's particularly ugly. So let me do one more. Let me clear the screen. I want to do one more problem that's phrased differently. And then I want to show you what happens when we move to 3 dimensions, just so you can see how the formula expands. And then that's it. So for example, let's use tangent plane approximation at a nice point. I'll be very specific, a nice nearby point to approximate. So I'm not going to give a function here because we'll have to figure it out. Let's approximate the sine of, say, 7 pi over 36 times the cosine of, sorry, I said 36 here, so let me write that in. And then we have the cosine of, say, 23 pi over 100. So this looks pretty tricky, right? It's not clear what the nearby point is, but these problems are generally designed to be pretty nice. So look at these two values that are here, right? 7 pi over 36. This is approximately 6 pi over 36, which is pi over 6. And that's nice. That's one we know. And 23 pi over 100 is approximately 25 pi over 100, which is pi over 4, which is nice. So what we'll do is we're going to define a function, f of xy, be sine of x cosine of y. And then what we're trying to find is f of 7 pi over 36, 23 pi over 100. That's the goal. Now, by the tangent plane approximation, that thing that we're looking for, let me write it out. This is approximately f at the nice point, pi over 6 pi over 4, plus f sub x at the nice point, times 7 pi over 36 minus pi over 6, plus f sub y at pi over 6 at the nice point. Again, this is just using the formula from the previous page, times y minus the nice y. So just like before, there are 3 things we need to find. This one, and this one. We haven't found any of them in this case. So that's all right. Let's work through these. So first, actually, let me do these in the upper right so that things are out of the way. And then we can put the answer below it. So f of pi over 6, pi over 4. That's sine of pi over 6, cosine of pi over 4. So sine of pi over 6 is 1/2 times the square root of 2 over 2. That's the square root of 2 over 4. And we find our derivatives, f sub x of xy, derivative with respect to x. So it has a comma in it that shouldn't be there. So it's a derivative of this thing just with respect to x. So y is treated as a constant. So this is cosine x cosine y. So f sub x of pi over 4, sort of pi over 6, pi over 4. This is cosine of pi over 6, cosine of pi over 4. Cosine of pi over 6 is root 3 over 2, times root 2 over 2 is root 6 over 4. then f sub y, that will be derivative with respect to y, so derivative cosine is negative sine, so I get negative sine x sine y. So f sub y of pi over 6 pi over 4 is negative sine pi over 6 sine pi over 4, which is negative. Sine of pi over 6 is 1/2 again. Sine of pi over 4 is again root 2 over 2. This is negative root 2 over 4. So we take all those things, go back down to the bottom, fill in the result. So we get root 2 over 4 plus root 6 over 4 times the difference between those. Again, I'm going to leave this just as a subtraction for now, but these are not hard to do. This is just so we can sort of see what we did better. Plus we have negative root 2 over 4, 23 pi over 100 minus pi over 4. And that's our final approximation. So that's really it, right? We find a nearby nice point, we have a function, we plug everything into the tangent plane approximation, we call it a day. So, final note then. In 3 dimensions, what happens? You can probably guess. I'm not going to do an example of this. I just want to illustrate this so you can see the pattern. Right? Really, this isn't tangent plane approximation. This is what we could argue is maybe like tangent space approximation. But what we would have is f of x, y, z is approximately f of x0, y0, z0. And then we run through all the derivatives. So we have the derivative with respect to x, x minus x0, plus the derivative with respect to y, times y minus y0, plus the derivative with respect to z, times z minus z0. That's what would happen. And in theory, you can go further. You can go to 4 variables, 5 variables. You just keep adding more. All of these generalize to higher dimensions, to higher derivatives, as like Taylor expansions and so on. But it's just enough to see the pattern, to understand these approximations are interesting, they're useful. They underlie a lot of what goes on in computers when they're doing approximations, calculating, and so on. So that is the end of that section.